Black holes are famous for swallowing everything that comes too close. But what happens when two black holes meet? They don't just swallow each other. They spiral together, faster and faster, until they become one. In the final moments, they release an enormous burst of energy, more than all the stars in the observable universe combined. This energy is not light. It is gravitational waves, ripples in the fabric of spacetime. For a century, gravitational waves were just a prediction of Einstein's theory of general relativity. Then, in 2015, LIGO made the first direct detection. Since then, we have observed dozens of black hole mergers. Today, we're going to explore these cataclysmic events, how they happen, what they teach us, and why they are among the most important discoveries in modern astrophysics. A cosmic dance. Black hole mergers begin with two black holes in orbit around each other. These are called binary black holes. They can form in several ways. Two massive stars might be born as a binary pair. When both explode as supernova, their cores leave behind two black holes orbiting each other. Alternatively, black holes can capture each other in dense star clusters. Once a binary black hole forms, the two objects orbit each other at enormous speeds. They are separated by a distance that can range from millions of kilometers down to just a few kilometers. Over time, they lose energy and spiral inward. This process can take billions of years, but the final moments are incredibly fast. Ripples in spacetime. According to Einstein's general relativity, any accelerating mass produces gravitational waves, ripples that travel at the speed of light. But these waves are extremely weak. A pair of orbiting black holes, however, produces waves strong enough to detect. As they emit gravitational waves, they lose orbital energy. Their orbits shrink. They spiral closer. The waves themselves stretch and squeeze space as they pass. Imagine a ripple moving through a pond, but instead of water, it's space itself. When a gravitational wave passes Earth, it alternately stretches and compresses distances by a tiny fraction, less than the width of an atomic nucleus over a distance of 4 kilometers. Detecting such a tiny effect is an engineering marvel. Slower and faster. A black hole merger has 3 phases: inspiral, merger, and ring down. During the inspiral, the black holes orbit each other at increasing speed. Early on, the orbit might take hours or minutes, but as they get closer, the speed becomes relativistic, a significant fraction of the speed of light. In the last few orbits, they are moving so fast that they complete dozens of revolutions per second. The gravitational waves emitted during the inspiral have a characteristic frequency that rises, a chirp. This chirp is like a cosmic siren. By analyzing the chirp, scientists can determine the masses of the black holes, their spins, and the distance to the merger. The inspiral phase ends when the black holes are separated by only a few times their event horizon, radii. A single black hole is born. The merger itself is the most violent moment. The two event horizons touch and merge into one. For an instant, the combined black hole is not perfectly spherical. It is distorted, like a lumpy blob. The merger releases a tremendous burst of gravitational waves, converting several solar masses of matter into pure energy in less than a second. That energy is equivalent to the mass of several suns turned into gravitational waves. To put it in perspective, the most powerful supernova releases about 10 to the power of 46 joules of energy. A black hole merger can release 10 to the power of 48 to 10 to the power of 49 joules, 100 to 1,000 times more. And it does so not over weeks or months, but in a fraction of a second. For that moment, the merger outshines every star in the observable universe combined, at least in gravitational waves. Settling into shape. After the merger, the newborn black hole is not yet stable. It is deformed. vibrating like a bell that has been struck. It emits gravitational waves as it settles into a spherical shape. This final phase is called the ringdown. The frequencies of the ringdown waves depend on the mass and spin of the final black hole. By measuring them, we can test whether the black hole obeys the predictions of general relativity. The ringdown lasts only a few milliseconds for stellar mass black holes, but it can be longer for supermassive ones. After the ringdown, the new black hole is calm, a perfect, featureless sphere. It will continue its existence, perhaps merging with another black hole billions of years later. Listening to the universe. LIGO, Laser Interferometer Gravitational Wave Observatory, consists of 2 detectors in the United States, one in Washington, one in Louisiana. Each detector uses laser beams to measure distances between mirrors with incredible precision. When a gravitational wave passes, it changes the length of the detector's arms by a tiny fraction. Virgo in Italy and Kagra in Japan provide additional detectors to triangulate the source. On September 14, 2015, LIGO made history. It detected gravitational waves from a black hole merger about 1.3 billion light-years away. The signal, named GW150914, matched the predictions for 2 black holes of about 36 and 29 solar masses merging into a 62 solar mass black hole. 3 solar masses were converted into gravitational wave energy. That discovery earned the 2017 Nobel Prize in Physics. A new window on the cosmos. Since 2015, LIGO and Virgo have detected dozens of black hole mergers. They have found black holes of unexpected masses, some as light as 8 solar masses, others as heavy as 90 solar masses. They have observed mergers of black holes with different spins and orientations. They have even seen a neutron-star merger, which also produces light and heavy elements like gold. These observations have revolutionized our understanding of black hole populations. We now know that binary black holes are common. We have measured the rate of mergers, about 1 per few minutes in the observable universe. We have tested general relativity to new precision, and we have opened a new way to study the universe, gravitational wave astronomy, which allows us to see events that are invisible to traditional telescopes. The future of gravitational wave astronomy. Black hole mergers are the most energetic events in the universe since the Big Bang. They are also among the most informative. Each merger tells us about the life cycles of massive stars, the dynamics of star clusters, and the nature of gravity itself. With new detectors coming online, including the space-based LISA mission, we will soon observe supermassive black hole mergers and events from the early universe. What is most remarkable is that we have only just begun. Before 2015, gravitational waves were a prediction. Now they are a routine tool. Every few weeks, we detect another black hole merger. The cosmos is singing to us in gravitational waves, and we are finally learning to listen. What do you think? Does the idea of space stretching and squeezing excite you or unsettle you? Let me know in the comments. Thanks for watching Daily Dose of Space. Stay curious, and I'll see you tomorrow.